Welcome to this video on the physical pendulum. In this video, we're going to be taking a look at how realistically, if the mass of the pendulum is distributed all the way from the axis of rotation, we have to take into account a few other factors. Now, if you haven't watched the video on the simple pendulum, you want to go back and check that out because it does explain a little bit of where we're going to come from in this video. So over here I have a wooden rod that's fixed on one end, and I have it here at some position theta from where it first started. So I just wanted to show it in two different situations. Now we're going to say that the restoring torque acting on this is going to be F cross R again, which is also equal to I alpha. Now in this situation we don't have all the mass located at the end, so the force is going to act at the center of mass, right? And we know that the force is really this force mg, but we are looking for this component, which is mg sine theta, which is the restoring component. We also know that it's acting at the center of mass, which in this case, if the length of the rod was L, then the center of mass would be equal to L over 2. Okay, so that's something we've got to play into here. We've got to say that the force, okay, might be mg sine theta. R now is going to be L over 2, not L, like it was in the previous example. Now in addition, I is not going to be mr squared. Now we could derive the expression for this, but we know from before that the moment of inertia of a rod about its center of mass is going to be 1/12 ml squared. So when I factor all of this stuff in here, I have mg sine theta times L over 2 equals 1/12 ml squared times alpha. Now again, we're going to do a small angle approximation, and the small angle approximation is going to say that the sine of theta is equal to just theta for small angles only. So when we have small angles, theta and sine of theta are the same, so I can change this from mg sine theta to just mg times L over 2 times theta equals 1/12 ml squared alpha. Now, other things can be factored and changed over here. We can see that one of the L's would factor out again, an M can factor out, and we can get this into a more usable form. However, let's say that this thing that was oscillating is kind of a little bit of a weirder shape. So maybe it kind of had a look like a guitar or a violin or something like that. Okay. Now what I'm going to do here is the moment of inertia is not going to just be L over 2 or any of this. So what I'm going to do is just kind of put it in more generic terms, and I'm going to say mg sine theta is still acting at the position R, center of mass. Okay, so I'm designating that's acting at the center of mass, and this is the moment of inertia times this angle. Now again, I'm going to say that this is still for a small angle approximation where sine of theta is approximately equal to theta. And what I can show here is that at very small angles, if I was going to set up my equation to solve the differential equation, I would have something like this. So mgr at the center of mass times sine theta equals I times alpha. I'll divide by I. Okay, and I'm going to go ahead and make the approximation for the angle. So I have mg r at the center of mass over I, so all of that is a constant, okay, times theta equals the angular acceleration, which I'm writing in as the second derivative of the angular position. Okay, so I see here that this again is going to be my angular frequency. Just like before, everything that was out front had some comparison or attachment to my angular frequency. And so the angular frequency here is going to be this value, mg RCM over I, but of course the square root of that to account for the similarities. So if we're going to write the period equation for a regular pendulum, we have 2 pi times root L over G. Here, if we're writing this, we're going to have T equals 2 pi times root. Now remember, this is angular frequency, so when we make it period, we have to flip this. Becomes root I over mg times the position at the center of mass. So you can see they're very similar. Again, the main thing that we're still accounting for is these small angle approximations. But we get this very similar equation where we can see how some things didn't cancel out when it's a little bit more of a complex solution to the same original idea.